Welcome back, AP Statistics. This is Chapter 18, Confidence Intervals for Proportions. So in the prior section, we talked about the idea of a point estimate. On page 471 of your textbook, if you recall, researchers find that 51.9% of a sample of 104 sea fans in Las Redes Reef off the coast of Mexico have some kind of disease. Suppose we wanted to estimate the true population proportion of all sea fans that are diseased. A decent guess would be 51.9%, but that's likely not the right answer. This is an example of a point estimate, which is a one-number estimate of the parameter. It's the best one-number answer we have because it's an answer we glean from a hopefully representative sample, but the issue is that it's probably very likely incorrect. We'd say the best point estimate for the population, though, as I've said, the population proportion in this case, is the sample proportion. That's the best we got. The true proportion might be 51.9%, but it's almost certainly not. And here's the big question. Can we do better? And it's at this point where we take this idea of an estimate and take it away from a point and talk about an interval. Interval estimates for parameters. Statisticians have found that a better way to answer this question is to construct an interval estimate that has a certain likelihood of, shall we say, catching the true population proportion. So our question is, what is the true population proportion of diseased sea fans? Statisticians prefer an interval estimate, creating an interval kind of like a net that has a certain likelihood of catching the true population proportion. We call this interval estimate a confidence interval. Depending on how we make our interval, we have a certain level of confidence, we say, that's a technical term, level of confidence that we will catch the true population proportion. Let's find out how to construct a confidence interval for the true population proportion, any one we would like. To construct a confidence interval for the true population proportion, we need to use some facts about the sampling distribution for a sample proportion. That is from Chapter 17, if you recall. Recall that the standard deviation for the sampling distribution of sample proportions, that's this fellow right here, this p hat, is equal to the square root of p times q all over n. Of course, we don't know what p and q are. If we did, then we wouldn't need to answer this question at all. So we're going to use p hat and q hat instead. All right, we're going to use p hat and q hat instead. All right, that's the best we got. Unfortunately, that's what we have to work with. If we knew what p and q were, we wouldn't need to find a confidence interval because we'd already know what the true population proportion is. So our modified formula is going to be the standard weight. What's with the E? Well, if we are estimating a standard deviation of a sampling distribution, we call that a standard error, all right? So we switch our notation a little bit. A standard deviation is a precise computation for the distribution of a random variable. Standard error uses a bit of sample data as a pretty good estimate, and that's what we have to work with. Now we're going to actually construct a confidence interval for the true population proportion. Using our formula for standard error, the standard error for p hat is going to be about 5%, a little shy of 5%. So our sampling distribution for the sample proportion would fit this model. If you remember from Chapter 17, we were able to use a normal model to describe the sampling distribution of a sample proportion. It's centered at the assumed population proportion, and we don't know what that is. We'll get to that in a moment. but it has a standard deviation of approximately 0.49. Now, admittedly, that is a guess. That's a standard error, but if our sampling is good, that's going to be pretty close. We don't know what P is. Of course, if we did, we wouldn't need to do any of this. But we do know, using the 68, 95, 99.7 rule for the normal distribution that's graphed before you on the left, that 68% of P hats, and let's just remind ourselves what that means. It means proportions for a sample of 104 C fans. So 68% of our sample proportions, say we were to sample many samples of size 104, 68% of those P hats, proportions of disease C fans, will be within one standard error of the true population proportion. 95% of the P hats will be within two standard errors of the population proportion, and 99.7 of the sample proportions will be within three standard errors of the true population proportion. So now we're going to change our perspective, and not gonna lie, this to me is one of the most brilliant things that statisticians have ever done. So I'll be done gushing. I just think this is amazing. We're going to change our perspective. If what I said on the last slide is true, then there is a 68% chance that the true population proportion is one standard error away from the sample proportion. There's a 95% chance that the true population proportion is two standard errors away from our sample proportion, and there's a 99.7% chance that the true population proportion is three standard errors away from our sample proportion. So if everything I said on the last slide is true, then those three facts are true as well. So now we can work with a normal distribution curve not centered at some unknown population proportion that we're trying to learn about, but centered at our sample proportion that is relatively much easier to find. So we can spread a net some number of standard errors from P hat and have a certain likelihood of catching, as it were, the true population proportion at some level of confidence. The wider the net, the more likely we'll catch the true population proportion. But if we make the net too wide, the more obsolete the interval becomes. For example, if I were to say, we're supposing that around half of these C fans are diseased. If I were to say that between 25 and 75% of these C fans are diseased, that's a pretty wide interval, and I am almost certain, unless our data are horribly off, I am almost certain to catch the true population proportion. But that net is kind of ridiculously wide. What use would it be? We want a small enough net that it gives us a pretty accurate idea of where the true population proportion is, but we don't want to make it too narrow, or else our odds of actually catching the population proportion go down. So it's a bit of a catch-22, and we'll talk about that. So we're going to continue our work constructing a confidence interval for P. Now that we have that change of perspective and we're working with a bell curve centered at P hat. The extent of our net on either side of P hat is called the margin of error, okay? The margin of error, that's the extent of our net on either side of the sample proportion, that net that we use to try to capture the true population proportion. The margin of error is equal to the number of standard errors we proceed out on either direction from the sample proportion times the size of the standard error, which we've already computed to be about 0.049. Relative to P hat, which is at the center of our bell curve, the margin of error that would be 95% likely to contain the true proportion of disease C fans is about 2 times our size of our standard error, which is about 0.1. Now, why the 2? Well, if you recall from the 68, 95, 99.7 rule, 2 standard deviations, or in our case, 2 standard errors, away from the mean of the distribution curve on either side would contain 95% of the area. And in statistics, area equals probability. Okay? So if we want a 95% chance of catching the true population proportion, we need to precede 2 standard errors out from the middle of the bell curve. And that interval will be 95% likely to capture the true population proportion. So using a margin of error of 0.098 or 9.8% approximately, we could construct a confidence interval for the true proportion. And that confidence interval would be between 42.1% and 61.7%. You can see my work on my bell curve down here. My curve is centered at the sample proportion, 51.9%. 2 standard errors to the left and to the right would give me an interval of 42.1% to 61.7%. This confidence interval is called a z-interval for the population proportion, that is a formal way of saying it, or simply a 1 proportion z-interval. Okay? In this context, z, as it is often, is shorthand for the normal model. Z is a nickname for the normal model, and we see that a lot in statistics. The interval means that we can be 95% confident that the true proportion of disease C fans is, in fact, between 42.1% and 61.7%. That's a decently wide interval, and you'll find with proportions that we need very, very large samples to get tighter intervals than that, but that is helpful. We can be 95% confident the true proportion is somewhere in there. Now, you've noticed that asterisk next to the word means, which might be a little concerning, but this is kind of what it means, all right? This is not technically, mathematically, what a confidence interval means, and you will need to know that technical mathematical definition of a confidence interval, and we'll get to that on the next slide, okay? So here we go. What does a confidence level like 95% actually mean? What is a confidence interval really saying? All right, now this gets pretty technical. So I have this image from the textbook that I found is helpful, and I will do my best to describe this. This does get a little messy. Okay, when we say that we have a 95% confidence that our interval contains the true proportion for the population, here is what we mean. 95% of samples of the size we are considering, in this case our sample size 104, will produce confidence intervals with the same number of standard errors in the margin of error, all things held equal, that capture the true proportion of infected C fans. Okay? Our interval could be one of the 95% that works, or it could be one of the 5% that doesn't. 95% of samples that we are considering will produce confidence intervals that capture the true population proportion, and 5% won't. That's what confidence level means precisely. Okay? So when we talk about confidence level, we're talking about the proportion of samples of the same size using the same number of standard errors in the margin of error that would capture the true proportion. All right, that's what our confidence interval is actually about. Okay? And we see in this picture below that there are many confidence intervals that are computed here. Each one of these little box plot looking buddies here is a confidence interval. We see most of them contain this green line. The green line marks the true proportion, which of course is going to remain constant. But some of these confidence intervals do not contain the true proportion, all right? Though most do. That's what a level of confidence is all about. We can be some proportion sure, some percent sure that we are going to catch that true population proportion with our sample, though we can never be completely certain, and that too is a theme of statistics. There is a practical interpretation. We are 95% confident that the interval between 42.1% and 61.7% captures the true proportion of infected C fans. Okay? So that is a practical understanding of what a confidence interval does. And admittedly, that makes a bit more sense. That's why people refer to it as a practical understanding of a confidence interval. Now, when we talk about confidence intervals, it is totally acceptable to say this. We are 95% confident that between 42.1% and 61.7% of C fans are infected. That is a casual interpretation, and that's really the payload. That's really the information we're after. Give me a range of proportions of infected C fans that's likely to contain, very likely, 95%, 19 out of 20 chance of containing the true population proportion. Now, why all these definitions? Well, let me let you in on a little secret. Actually, it's not a secret. It's public knowledge. There is going to be, I will guarantee it, if I were a betting man, which I'm not, I would bet money on the fact that you will have a question on the AP test, at least one, maybe more, that has you analyze a confidence interval and the question says, what does this mean precisely? And what they'll be looking for is this formal definition, the first definition, all right? There are going to be several answers, some of which will sound like this first definition, but you need to know this first definition. I can guarantee you will see it on the AP test at some point. I have done a lot of AP practice. I have given a lot of AP practice to my students. It's going to happen. You can bank on it. So let's interpret a confidence interval now. Let's apply our knowledge. Here's one from the textbook. In January and February 2016, Pew Research polled that many U.S. adults, asking them, how often do you read the newspapers in print? I can almost guarantee this proportion has gone down, unless there's some newspaper renaissance in, I don't know, somewhere. For the first time, a majority of adults responded hardly ever or never, all right? These days, it's probably never. If anything, that proportion has gone down. It is standard among pollsters to use a 95% confidence level unless otherwise stated. Given that, what do these researchers mean by their confidence interval in this context? Okay, what precisely do they mean? Okay, think about it, pause the video, and unpause the video when you think you have an answer. All right, I'll assume we're ready to continue. Let's look at the answer. If this polling, says our textbook, correctly of course, were done repeatedly, 95% of all random samples would yield confidence intervals that contain the true proportion of all U.S. adults who hardly ever or never read the newspaper in print. All right? So with repeated polling, 95% of samples we would collect would yield confidence intervals that work, that predict the true population proportion, or that contain it in the interval, we would say, correctly. All right? That means 5% won't. That is technically what a confidence interval is all about. So here we go. We now have a confidence interval and a bunch of possible interpretations. Some are going to be right. Some of them are going to be wrong. Let's see. A Pew Research study regarding cell phones. Ask questions about cell phone experience. There's Pew Research again. Pew and Gallup, they are the gold standard for sampling, surveys, statistics about the public in the U.S. and abroad. One growing concern is unsolicited advertising in the form of text messages. Yes, that is a concern. I agree. Pew asked cell phone owners, have you ever received unsolicited text messages on your cell phone from advertisers? Yes, every 4 years, predictably. If you know, you know. And 17% reported that they had. Pew estimates that a 95% confidence interval is 0.17 plus or minus 0.04. That is a way of expressing a confidence interval. The sample mean from their, I'm sure this is Pew Research, very large sample, is 17% with a margin of error of 4% on either side, or between 13 and 21%. All right, if you add and then subtract 0.04 to 0.17, you would get 13% on the left and 21% on the right. Easy enough. Are the following statements about people who have cell phones correct? Explain. Read 1 through 5. Do note that 3 doesn't end with the phrase phone owners. It continues on the other side. Try numbers 1 through 5. See if you agree with that interpretation of the confidence interval. And if you don't agree with it, why don't you agree with it? Try these on your own, pause the video, unpause the video when you've tried all 5 problems. Okay, I'll assume we're ready to continue. Let's look at number 1. In Pew's sample, somewhere between 13 and 21% of respondents reported that they had received unsolicited advertising messages. This is a bad interpretation. The confidence interval makes a prediction about the population, not a sample, all right? This is not ultimately about the sample. We use the sample to estimate the population, all right? We're trying to find the true population proportion. Also, there's no guessing about the sample proportion. We know it's 17% because literally in our problem, you look at the confidence interval, the interval is centered at 17%. We don't need to say somewhere between 13 and 21%. That is factually true, but that's beside the point. We know what the sample proportion is. It's 17%. You don't need to guess about that. So let's look at number 2. We can be 95% confident that 17% of U.S. cell phone owners have received unsolicited advertising text messages. This is not a good interpretation. We can be 95% certain that the true proportion is contained in the interval, not equal to 17%. 17% is a point estimate. A point estimate is the best one-number guess at the true population proportion, but the rough part about point estimates is they're almost certainly wrong, and we have no way of knowing how wrong they are, okay? It's just the best one-number guess we got. The 95% confidence refers to the confidence interval, not a point estimate. Let's look at number 3. We are 95% confident that between 13 and 21% of all U.S. cell phone owners have received unsolicited advertising text messages. So we're 95%. That interval we found is containing the true population proportion. And that is a good example of the casual interpretation of a confidence interval. There is nothing wrong with that. 95% certain between 13 and 21% of all U.S. cell phone owners have in fact received unsolicited advertising text messages. That's a casual interpretation. Nothing wrong with that. We could be more precise, but it's not required. Number 4, we know that between, we know. That phrase alone should make you think that this is a bad explanation. Statistics is not as much about knowing things as it is making predictions. Having perfect knowledge of something is something we rarely have the luxury of in statistics. All right, I could have said that better perhaps, but you get the point. Those words "we know" that immediately makes this suspect. So we know that between 13 and 21% of all U.S. cell phone owners have received unsolicited advertising text messages. Yeah, that's bad. We don't know anything about the true proportion with perfect certainty, all right? That is not a good interpretation. And number 5, if you chuckled a little bit at number 5, I did too. 95% of all U.S. cell phone owners have received unsolicited advertising text messages. That's probably true today, but might not have been true when this Pew Research study was happening. And yeah, this is a bad interpretation. 95% refers to the level of confidence for the confidence interval, not the proportion of cell phone owners who have received unsolicited messages. And if you thought this answer was funny, my use of a double comma in my answer is also kind of hilarious too.